Hey everybody, we're going to be discussing selecting the right fuels and the properties of fuels. So first off, let's talk about selecting the right fuel. Several factors need to be taken into account when comparing fuels. The efficiency of a fuel is a combination of many factors and cannot be measured by one characteristic. Some of the following factors that may need to be considered are: 1. The amount of heat released per unit mass or unit volume of the fuel. This is the heat of combustion. A higher amount of energy released doesn't necessarily indicate a better fuel. In some cases, a fuel that releases a low amount of energy may be adequate. This table shows the heats of combustions. Notice that they're in per units, right? So kilojoules per gram, kilojoules per liter, kilojoules per mole. So they've written in this way just to demonstrate, I guess, in this way that there's a unit per mass or a unit per volume, which is all relatable. This table shows the heats of combustions of various fuels. For these fuels, the amounts of energy are for complete combustion, the products being carbon dioxide and water. Remember, combustion is fuel goes to carbon dioxide and water once it's been burned. Just remember that molar volume describes the relationship between standard conditions and the volume of a gas. The energy density is another factor that we have to use to consider the right fuel. This indicates the amount of energy released per kilogram of fuel. Transport may be a major cost in supplying a fuel. The higher the energy density of a fuel, the more cost effective it is to transport. Another factor is the ease of transport. How easy a fuel is to transport will be determined by such things as whether the fuel is solid, liquid, or gas. Highly volatile fluids may require specialized containers. Some dangerous fuels can only be transported along designated routes and cannot travel through residential areas. Some fuels can be easily transported using permanent pipelines. In Australia, most of our electrical power stations are coal-fired, while in other countries, oil or natural gas use is most widespread. Many of our power stations are built within easy access to coal mines to reduce transport costs. So here's one that I'm really passionate about. It's the environmental concerns, including methods of obtaining fuel, for example, mining, transport, and waste products created as the fuel is used. Some fuels are considered cleaner than others, and special precautions need to be taken when using dirty fuels. So look at some of the properties of organic molecules. Organic molecules, of course, are carbon compounds. Okay, if it has a carbon compound, it is an organic molecule. Carbon compound. Okay, so one thing about carbon compounds is they all can be burned. Combustion means burns, so combustion. It burns. It goes from fuel, be it wood or oil or coal, to carbon dioxide plus water. And it also generates heat. Let's look at the boiling point of organic molecules, okay? Boiling point is the energy necessary to separate the molecules' intermolecular forces from each other. So in this case, it's van der Waals forces. Okay, so in this case, let's just pretend that there's some carbons here, and there's some hydrogens, like so. Okay, so there's going to be, let's call them London dispersion forces. A London dispersion force is something like this, okay? So if we took an instantaneous snapshot, click, ching, of a hydrogen molecule, okay? So at one point, this electron is going to be in this region of the hydrogen, okay? It only has one electron. It's floating around here. This area where the electron is has what's called a partial. That's the symbol. That's the symbol for partial negative. However, in this side right here, partial positive. However, if we were to take another instantaneous snapshot, what we might find is that the electron is here, which gives this area, because it's an electron, it's negatively charged, a delta negative, a partial negative charge, and this one has a partial positive charge. So this only happens instantaneously, and it happens, but there is this negative charge, this partial negative and partial positive charge. Well, let's say that there's another molecule, a hydrocarbon that's floating around, and we have another hydrogen right here. And in this case, the electron's floating around right here in this instantaneous snapshot. Well, this is a partial negative. They actually are going to attract one another for a period of time. And this would be the partial positive over here in this section. Okay. These intermolecular forces means forces between the molecules, are actually going to attract to each other. And this contributes to the boiling point of organic molecules. All right, let's do it the organic chemist way instead of always drawing it out this way all the time. And this is just so that we can get an idea of what I'm talking about here when we're talking about boiling points. Instead of drawing it out this way every time, so there's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. This is pentane. Instead of drawing it this way, I'm going to draw it out this way. 1, 2, 3, 4, 5. Now, we don't normally put the numbers here, but this represents carbon 1, this represents carbon 2, carbon 3, carbon 4, carbon 5. And we just imagine that the hydrogens are there, okay? So, the intermolecular forces, the London dispersion forces, are the weakest of the forces, and that's because they only have that partial positive, partial negative for a brief amount of time. Well, if we had two, now we know where these numbers represent. Let me get rid of them real quick here. Okay, let's just draw out another one. So let's just draw out another one. Okay, so there's going to be hydrogens here which can interact with one another, okay? Well, if we have longer chains, pentane actually has 36-degree boiling point, okay? Well, let's draw out hexane. 1, 2, 3, 1, 2, 3, 4, 5, 6, another hexane. We've added just one more carbon with those hydrogens that are able to interact with one another, and we now have a 69-degree boiling point. The longer the hydrocarbon chains, the more attracted that these molecules are to one another, the more energy it takes to pull apart. The energy being heat, and this means higher boiling point. When the molecules have a low boiling point, that's we're talking about volatility here. So how likely they are to evaporate, volatility. Okay, the volatility relates to the flash point. The flash point of a volatile material is the lowest temperature at which vapors of the material will ignite when given an ignition source. The flash point may sometimes be confused with autoignition temperature, which is the temperature at which the vapor ignites spontaneously without an ignition source. So it gets so hot that it reacts with oxygen and it starts to combust. This is related to the boiling point. So just to clarify, a volatile compound has a low boiling point. Small molecules have London dispersion forces and will be very volatile. Polar molecules have extra intermolecular bonding, which lowers the volatility. This makes them less volatile than alkanes and alkenes and alkynes.